Hello everyone. Today we will be presenting our project on thermal management and optimization of the pin-fin heatsink. This work was completed under the Heat and Mass Transfer course ME334, and it was guided by Professor Soumyadeep Seth, and it was under the mentorship of TA Mondeep. And our team members include Sai Gauri, Kushagra Shahi, and me, Siddesh Patil. So in this presentation, we will be covering 6 major sections. Like, uh, let's see what are they. So let's see what is the problem statement for the project. So modern CPUs generate very high heat over a small area, so they require efficient cooling. So for this, we will be using pin fins. So before diving into why are we using pin fins, we will have to see why pin fins work so well. So pin fins offer very large surface area in compact volume and a multi-directional airflow, path enhanced heat transfer even at the moderate air velocities, but their effectiveness strongly depends on the geometric choices. Too few fins or is cooling is very weak, and too many fins the air cannot pass through, choking the system. So optimization in this parameters is very essential. So optimizing geometry improves heat removal while reducing material and weight. Now let's see what is the project problem. So the dimensions given are of the CPU are 4 centimeter into 4 centimeter, and it generates 100 watt heat. So its temperature must stay below the 85 degrees Celsius. The heat sink base is 4 centimeter cross 4 centimeter, and it is made up of aluminum, and it is cooled by forced air, which is at temperature of 25 degrees Celsius, which is having H equals to 150 watt per meter square Kelvin on all exposed surfaces. So the goal is to simulate how fin geometry affects the base temperature and identify the best design, like how many fins and what parameters we should use to optimize this best design. Now let's see the theoretical background behind this problem. So we will first calculate the resistance for a single fin. So real fins are not at the uniform temperature. So they are not at the single base temperature. They become cooler towards the end. So they are less effective than the ideal fin. So their efficiency is not 1. So this fin efficiency reduces the effective surface area available for convection. So we'll first calculate the thermal resistance for one fin. And for this mathematical modeling, since we did not have the fin tip temperature, so we have used the insulated fin tip equation, and we have used the corrected fin length LC to take into correction. So the fin efficiency can then be defined as tan h of MLC upon MLC, where LC is the corrected fin length. Then the resistance of single fin then we defined as delta T upon Q, that is 1 upon eta efficiency into H into area of one fin surface. And since this all fins are attached to the same base and transfer heat to the same ambient air, they can be considered as connected in parallel. This is the total heat conduction. Now we'll see the total resistance for all fins which are in parallel. So obviously there will be R single fin upon N, like number of total fins, as they reduce their total resistance. And substituting the single resistance for single fin, the R fins is given by 1 upon number of fins into fin efficiency into H into area of fin surface. So this 1 upon R, that represents the total conductance of the fin array, and the diagram is also given. And the parallel combination of fins and base. So all the fins and the base, and resistance offered by all the fins and the resistance offered by the base area, which will be total area minus number of fins into single fin cross section area, will also be in parallel. Hence the net resistance will be given as R fins into R base convection upon R fins upon R base convection. So the final relation will be like delta T, TB minus T infinity equals to Q into R net, which is given above.
We now present a parametric study on the effect of the number of fins, fin height, and the fin diameter on the maximum base temperature. We now investigate the effect of increasing the number of fins on the maximum base temperature. As we can see, as we increase the number of fins, the base temperature drastically decreases. But at the same time, this effect diminishes after a certain point. For example, increasing the number of fins from 225 to 256 only decreases the base temperature by 3 degrees Celsius. But this increases the material volume by a lot and thus makes a design expensive. So our goal here is to find a optimum point wherein the number of fins are just sufficient to keep the base temperature below 85 degrees, and at the same time the material volume remains low. Similarly, we also performed a parametric study on the effect of increasing the fin height at a fixed fin diameter of 2 mm. Let us zoom into our area of interest. Let us now focus on the effect of increasing the fin height when the number of fins is kept at 144. Similar to number of fins, we can see that as we increase the fin height, the effect on base temperature diminishes. It is evident that increasing the fin height beyond 35 mm for 144 fins is not beneficial, as it increases the material budget but has no significant effect on the base temperature. The reason for this is because the fin tip with increasing fin height has already become so cool that it does not enhance the heat dissipation by a lot. Apart from the number of fins and the fin height, we also performed a parametric study on the effect of increasing the base diameter. And we present the parametric study for increasing the base diameter with different number of fins. But as the problem statement uh, stated us to keep the fin diameter fixed at 2 mm, so we do not optimize our design for diameter. Here we provide a 4D optimization chart wherein the temperature is a function of height, fin diameter, and the number of fins. The color of each of the points represents the base temperature, and the three axes represent the three variables. Although in our present study we are not optimizing the fin for the fin diameter, but this study can later be used when the fin diameter is not fixed and can be used to optimize the fin diameter, fin height, and the total number of fins altogether. Based on the parametric study, we have decided to keep the number of fins as 144, which will be a 12 cross 12 array, the fin height to be 35 mm, and the fin diameter, which was fixed, to be 2 mm. Let us now see why have we chosen 144 number of fins. First reason is airflow choke. Whenever the number of fins increases, the spacing between each fin decreases, and this can make the air totally bypass the heatsink, as standard fans cannot push the air in. Secondly, we did not want to over-engineer our design. The requirement was only to keep the temperature below 85 degrees Celsius, and the present design already keeps it at a 30 degrees margin. So increasing the number of fins was not found suitable and feasible. And lastly, increasing the number of fins also makes the manufacturing of the heatsink expensive. And at the same time, it adds more weight on the motherboard mounts. Thus, due to these reasons, we chose number of fins to be 144. Let us now see why have we taken the fin height to be 35 mm. Firstly, keeping the fin height at 35 mm provided a 30 degrees margin to the design, and this keeps the design safe from cases when the surrounding temperature rises or dust accumulation decreases the heat dissipation. Secondly, increasing the fin height beyond 35 mm was adding more material to the design but was not reducing the base temperature a lot. So this was increasing the material budget but was not giving us any tangible outcomes. Third, increasing the height more than 35 mm would increase the aspect ratio more, and this would risk the fins to be bent, have fatigue, or also have structural failure. And finally, having very large fins would not be suitable to be mounted in standard electronics enclosures. Thus, due to these reasons, we chose the fin height to be 35 mm.
Now let's see the ANSYS simulation on final design which we get from the parametric study. So here we can see the pin fin model with 40 cross 40 mm base and 144 pin fins. The pin fin has 2 mm diameter and 35 mm length. The number of pin fin and the length of pin fins is decided on the basis of parametric study. We created this model in Autodesk Fusion and then imported it into ANSYS steady state thermal. Here we can see the mesh model. Since the model has many fins, the tetrahedral meshing was used. It has 4,46,085 nodes and 2,07,943 elements, which is sufficient for achieving good results. The analysis was steady state analysis, and we applied 6.25 into 10 to the power minus 2 watt per millimeter square uniform heat flux on the bottom face, and convection on all other surfaces with convection coefficient of 150 watt per meter square degree Celsius and an ambient temperature of 25 degrees Celsius. Also note that we get the heat flux from the heat generation by dividing with surface area. Now let's see the temperature distribution. So here we can see the temperature counter on the model. We can observe a gradual reduction in temperature from the base to the tip, confirming effective heat dissipation. We obtained a base temperature of around 57 to 58 degrees Celsius, which agrees with theoretical result within an error of approximately 4%. Now let's see the temperature counter and measure the base temperature in ANSYS steady state thermal. Here we can see the temperature distribution along the fins. Now let's check the base temperature. Here we can see the base temperature is between 57 to 58 degrees Celsius. We have successfully designed the pin-fin design, which successfully keeps the base temperature below 85 degrees Celsius, taking into account the risk of air choking and keeping the material cost in check. And also we have successfully verified the design using ANSYS Mechanical. Thank you.